So we've now reached our occipital lobe clinical correlation known as homonymous hemianopsia or homonymous hemianopia. Either are acceptable. And this condition is defined as a loss of visual perception in one half of the visual field. Now, I could sit here and spew a ton of random words describing this condition, but the easiest way to get a meaningful understanding of damage here is for me to draw it out and narrate as we go along because, as you'll see, the key to truly understanding what is meant by the words homonymous hemianopsia or homonymous hemianopia lies within being able to map out the neuronal pathway leading to the cortex in the occipital lobe and recognizing which of these specific neurons is responsible for which half of the visual field. There's going to be a lot of moving parts here, so in order to provide a mental outline, the flow of what we're going to cover will be as follows. We're first going to lay out the major components involved. Then we'll trace the neuronal pathways that project between these major components. Then we'll finally place a theoretical lesion in the occipital lobe, as well as in the projection to the occipital lobe, and discuss what sort of problem this causes. So let's get started. This animation will be considered from a superior perspective, as if you're above the head of the person we're drawing, and they are looking directly out in front of them at the Mardi Gras parade, representing the patient's visual field that we've drawn at the top of the page. Next, you'll notice the two circles marked L and R, which represent the patient's left and right eyes, as well as the retina for each eye. Moving caudally from here, you'll notice the area denoted LGN. This will represent the left and right lateral geniculate nucleus of the thalamus. Finally, you should recognize the squares labeled as the left and right cortex of the occipital lobe, which, if you'll remember, is the entire purpose of our discussion here. So now we're ready to show how neurons form a communication network between these areas. First, we'll draw solid, thin red and blue lines to represent where light coming in from the left and right halves of the visual field falls on the retina. Notice that the retina within each eye is split into nasal and temporal halves, and that these areas are color-coded to the visual field at the top of the page. From here, we'll make a thicker, solid red line, which represents the axonal projection from the temporal retina of the left eye to the left lateral geniculate nucleus of the thalamus, where it makes its first synapse. It's important to note here that the nomenclature changes from the optic nerves rostral to the optic chiasm to optic tract caudal to the optic chiasm, since we're now in the central nervous system. Likewise, we'll use a dashed red line of the same thickness to show the axonal projection from the nasal retina of the right eye to the left thalamic LGN. And be sure to observe this crossing or decussation from the right eye to the left thalamic LGN. This will become important when we lesion the cortex a bit later. So at this point, we have light coming from the right half of our visual field, falling on both the temporal retina of the left eye and the nasal retina of the right eye, where each of these areas of the retina send axonal projections to synapse on the left LGN of the thalamus. So, where do they travel next? From the left thalamic LGN, the synapses formed from both the ipsilateral and contralateral retinas send projections to what's called the primary visual cortex of the left occipital lobe, which is why we're talking about all of this in the first place, right? This projection from thalamic LGN to primary visual cortex is highly conserved and known as the optic radiation. For completeness, we'll quickly trace the same pathway on the contralateral side in blue here. Note that the neuronal projections from the nasal retinas of both the left and right eye form a nice decussation or crossing or X, which is precisely why the optic chiasm is named as such. Another way to think about this is that the projections to the LGN from the temporal retinas remain ipsilateral, while the projections from the nasal retinas cross midline and become contralateral. Now that we have completed the elements within our pathway, let's place a lesion within it and try to figure out what the deficit will be. So try to take a moment on your own to anticipate where in the visual field vision will be lost if a lesion like a stroke, or a tumor is placed here in the cortex or even in this optic radiation. Okay, so follow the pathway backwards from the occipital lobe cortex rostrally to the left thalamic LGN. We know that the solid red line from this LGN leads to the temporal retina of the left eye, but remember that the key to understanding this deficit is unveiled by the understanding of the decussation that occurs, where the dashed red line crosses in the optic chiasm, creating a pathway to the nasal retina of the right eye. Remember, the word homonymous indicates that both eyes are involved, so if you're able to reason that the lesion pathway in the left occipital lobe originates from the ipsilateral left temporal retina and contralateral right nasal retina, and if you also knew that the left half of each retina receives incoming light from the right visual hemifield, then you would be able to infer that these areas transmit light from portions of the right half of the visual field. So if you chose the right half of the visual field, you'd be correct.